Welcome to the Soil CRC's Building Technical Capacity for Improved Soil Management webinar series, Demystifying Soil Organic Matter. In this video, Murdoch University Professor Dr. Richard Bell shares key observations about the role of organic matter in soil. The information presented is sourced from the Soil Quality series of ebooks, specifically book number 3, Soil Organic Matter by Francis Hoyle and Daniel Murphy. Dr. Bell explores highlights from the book, including the importance of organic matter for ecosystem services, the cycling of soil organic matter, understanding the carbon to nitrogen ratio, and managing and monitoring soil organic matter. The information is from the perspective of Southwestern Australian soil research and study, nonetheless will benefit farmers, agricultural professionals and students everywhere. Here's Dr. Richard Bell.
Okay, so shall we kick off? For Western Australians, I think the challenge of soil organic matter is summarised in this quote from the ebook, which says, "Land clearing for agriculture has led to a loss of soil organic matter over time in many West Australian soils. Continuous cropping and soil disturbance linked to historic farming practices has resulted in significant losses of organic matter associated with faster decomposition and erosion." So a couple of key dot points. That soil organic matter is critical for soil ecosystem services and is an important part of the natural capital of a soil material. Soil texture, in particular the clay content of a soil, determines the potential for organic matter to be retained in a soil, but climate, which affects growth and biological productivity, drives the inputs and losses of organic matter in the soil. Across landscapes, you can get big variations in organic matter, both at small scales and large scales. So there's the challenge of sampling. The next dot point is that building organic matter in soils is a slow process. It's an incremental process, but it's worthwhile because we know organic matter provides many biological and chemical fertility benefits for soils. The organic carbon in soils in Southwest Australia has been mapped to some extent. This figure here shows areas where they have reasonably good records of the organic matter level, but you can see that there are large areas where we just don't have enough data to say for sure. But what we can see already is that close to the coast, where the rainfall is higher, the stocks of carbon in the soil are higher than as you go inland into the drier areas. And that tells us that the rainfall is really a big driver of what's going to happen here. And from the work that Dan Murphy and his group have done, they've looked at which parts of the state already have close to the potential amount of carbon in the soil based on climate, and which areas seem to have the potential to grow more carbon because of higher rainfall. And you can see that what they're suggesting is that in these drier northern warmer areas of the wheat belt, the potential to build soil carbon is probably somewhat limited compared to the wetter coastal areas and southern zones. So here's a little video.
Over 1,300 soil sites across the southwestern agricultural region of Western Australia were assessed for a range of soil properties and site variables to determine the factors associated with changes in total soil organic carbon to a depth of 30 centimetres. Site variables including soil type, bulk density, clay content, pH, electrical conductivity, water repellence, disease, long-term climate data, and on-farm management information, such as nutrient application rates, stocking history, rotation, and use of amendments, were used in a meta-analysis to determine the primary drivers for measured differences in soil organic carbon. Analysis indicates that temperature and rainfall are primary factors influencing the variation in soil organic carbon content for Western Australian farming systems. Data shows higher soil organic carbon stocks are associated with increasing rainfall, a primary driver of plant productivity. In low rainfall environments, the potential to influence soil organic carbon stocks is more constrained when compared to higher rainfall environments, which demonstrate a wide range in soil organic carbon values associated with soil type and management. While unravelling the influence of geographic position from rainfall and temperature is difficult, data suggests environments with an average annual daily temperature of more than 17 degrees Celsius are limited in their capacity to accumulate carbon in soil, showing a narrow range of carbon values. Sites where average daily temperatures are below 17 degrees Celsius show a wide range in soil organic carbon values, which indicates a greater potential for management, soil type, and smaller scale climate variables to influence soil organic carbon. Results from this study suggests the capacity of environments with an average annual rainfall of less than 450 millimetres and an average daily temperature higher than 17 degrees Celsius are limited in their capacity to accumulate carbon in soil. As shown on this map, the highest potential for future carbon storage is associated with loamy soils and higher rainfall environments capable of supporting higher net primary productivity.
So, if we look at soil profile, we find that most of the carbon is in the upper layer, the upper 10 or 15 centimetres. In fact, 60% of the organic matter in the upper 30 centimetres is in that 0 to 10 centimetre layer. And of course, it's subject to loss there from erosion and from decomposition. The organic matter in the soil is actually a complex mix of different materials. So it's not a single material. And those different materials have different origins and different composition. So a portion of the organic matter in the soil is what we call dissolved organic carbon. And while it's only a small proportion of the overall soil carbon, it's quite an important pool for biological activity, microbial activity, that this is the carbon that often is driving a lot of the activity of bacteria and fungi in soils. So much so that in some places they measure the dissolved organic carbon level in the soil as an indicator of biological activity. Of course, a large portion of the carbon in the soil, the organic matter, is the humus. But there's also the particulate matter, which is an intermediate form of carbon that's in the process of being broken down into these more resistant and humus fractions. And that brings us to this little animation here, which is about the cycling of soil organic matter. So I'll play that.
Soil organic matter cycles continuously between its living, actively decomposing, and more stable fractions. When plants and animals die, they are decomposed to become part of the soil organic matter. Soil organisms fragment and consume organic residues, gaining energy to grow and reproduce. Fresh residues are broken down into smaller pieces and become part of the particulate organic matter fraction. As the material is further decomposed, a proportion of more biologically stable material enters the humus pool. Nutrients and other compounds not required by microorganisms are released as a result of this transformation and can then be used by plants. As the organic residues continue to decompose, a very small proportion becomes chemically stabilised, enabling it to resist further change. Again, nutrients superfluous to microbial requirements are released and are made available to plants. Nutrients resulting from organic matter transformations can supply up to 80% of the plant's requirements. Carbon dioxide emissions result from these biological transformations.
I should stress here that what we're talking about here is organic matter cycling in a soil as part of the natural ecosystem processes of soils. It's about adding additional carbon in the form of compost, which is able to generate new processes that perhaps don't occur in the natural soil. It's also worth mentioning that something like 2 to 4% of this organic carbon in the soil turns over or breaks down each year. So if you don't continually add carbon into a soil, the level is going to gradually decline because of this natural decomposition process. So even to maintain organic matter levels in soils, we've got to be adding as much as is decomposing just to retain the steady state of the current situation. Why are we interested in organic matter in the soil? Well, it's because it's involved in various biological functions, chemical functions, and physical functions, all of which go towards a healthy soil. Fundamentally, organic matter is an energy source for biological processes. So bacteria and fungi, even the fauna in the soil, are consuming this material as their energy source in order to live and to carry out their other functions. The organic matter in the soil is a store of nutrients, particularly nitrogen. Almost all of the nitrogen is stored in organic matter. Much of the sulfur is stored in organic matter. And what's commonly not understood is that quite a lot of the phosphorus in the soil is also stored in organic matter. And this organic matter contributes greatly to soil resilience, the ability of the soil to cope with stresses, droughts, and other disturbances and retain its function. Chemically, the surface area of organic matter helps with the retention of nutrients. Per unit weight of organic matter, it has a very high surface area, and that allows it to interact with nutrients and hold on to nutrients, particularly cations. The organic matter helps with the buffering, pH buffering of a soil. Where there are heavy metal or pesticide contaminants, it can help with immobilization. In the case of herbicides, for example, the breakdown of many herbicides by microorganisms in the soil is achieved because the microorganisms simply use those compounds as energy like any other carbon compound in the soil. And then the physical functions of soils, its formation and stability of structure depends on organic matter, and of course the water retention of the soil. So all of those. One of the key properties of organic matter, particularly organic matter that's being added into the soil, is its carbon to nitrogen ratio. In soils, the carbon to nitrogen ratio is generally in the order of about 10 to 12. So if you do a soil test and you compare the carbon and the nitrogen levels, you'll find the ratio comes out at about 10 to 12. But when we add material to the soil, it may have vastly different C to N ratios. Legume, stubble or residues have relatively low carbon to nitrogen ratios. grass legume pastures, somewhat intermediate, whereas cereal residues, oats and wheat, have quite high carbon to nitrogen ratios, and that can result in immobilization of nitrogen in the soil, because as those high C to N ratio materials are decomposed, the microorganisms actually consume available nitrogen from the soil temporarily. And the photograph here shows these strips of yellow coinciding where the crop residue from the harvester was dropped in the previous year, producing a high load of high C to N ratio material that is temporarily immobilizing that nitrogen. Of course, that nitrogen will eventually come back into the soil mineral pool as the microorganisms decompose. I mentioned cation exchange capacity. Soils may only contain 1, 2, 3% organic matter, and yet that tiny amount of organic matter can have a very major influence on the overall cation exchange capacity of the soil, as shown in this table here, which is cation exchange in units of charge per 100 grams of soil. So you can see sands and sandy loam textures, they have quite low cation exchange capacities compared to clay soils. But per unit weight, organic matter and humified organic matter have extremely high cation exchange. And that's related to their surface area and also the chemical compounds or molecules that are present on the surface of the organic matter that help it to hold on to cations. So there's quite a lot of material in this ebook, and I'm just picking out a few highlights here because we don't have time to go through it all, but I would encourage you to read it yourself from cover to cover. Storage of water in the soil is one of the functions of organic matter, because organic matter can hold several times its own weight in water. So if we were able to increase the organic matter of content of a soil from 1% to 2%, we would hold an extra 2 to 5 millimeters of water in the soil. So when we think about 5 millimeters of water, that's has the potential to produce an extra 100 kilograms of grain using 20 kilograms of grain per hectare per millimeter of water, which is the standard figure that we use in the French-Schultz equation. So that looks quite promising, but in order to increase the organic matter content of a soil from 1 to 2%, we would need to add something like 100 tons per hectare of organic matter, because most of that is going to decompose and leave only a fraction of that 100 tons in the soil to provide that function. So whilst we do know organic matter is important for holding water in soils, we shouldn't overestimate the potential for increasing water content by small increases in organic matter content of the soil. I'm going to skip over a few of those pages. Another of the important concepts, I think, in this book is about what we call attainable organic matter content and potential organic matter content, as opposed to the actual organic matter content. So the actual organic matter content is what's in the soil today under the current management. The attainable organic matter content is based on the climate in which that particular site or soil actually exists. So it's about the radiation, the temperature, the rainfall. And then the potential organic matter content is what you could hold in that soil based on its clay content, its bulk density, its mineralogy, and its depth. So in most cases, what we're looking at is changing management to increase from actual to attainable soil organic matter content. We probably can't go to the potential organic matter content unless we're in a system that's applying a lot of organic inputs such as compost, or we're changing the effective climate through irrigation. The next important concept I'd like to stress to you is this concept of soil organic matter balance. It's about outputs and inputs, and I'd just like to show you this little video.
I'm often asked why soil organic matter levels are different in different soils. If we think about a soil, the pieces of plant material that drop on the soil start to get broken down by microbes. The amount of organic matter that enters the soil is very dependent on plant productivity. And if we think about this as a tipping scale, on this side we have the amount of plant production, and that's very much related to the type of crop we're growing, so the amount of biomass that it produces, the climate, so how much net primary productivity can be grown, and of course how much we offtake in terms of a product from an agricultural aspect. On the other side of the tipping scales, we have the microbes, and they're using that organic matter as a food source. So they're breaking down plant residues as they enter the soil. The other loss mechanism is erosion, whether that be by wind or water. So at any given point in the field, the organic matter levels can vary through seasons and through years, depending on the inputs and the outputs. The other thing we need to think about is soil type. Not all soils are the same. Some soils have more clay, and the important aspect of clay is that the clay physically protects the organic matter from breakdown. Microbes cannot eat through the clay platelets to get to that organic matter. So soil type is certainly an important aspect, as well as the inputs of plant material and the rates of microbial breakdown.
The management factors that influence soil organic matter: net primary productivity. This is very much around climate and other aspects of soil management, whether we're dealing with crops or pastures, whether we're adding green manures or cover crops into the farming system, what the strategy is for stubble retention, whether we're controlling erosion, and what other soil disturbance events are occurring in that farming system, and finally, whether in the farming system there are organic amendments or inputs in the form of compost. The final thing I'd like to leave you with is carbon stocks can take a long time to build up. And this is an example here from a case study on the Esperance Sand Plain. And it was a study done by UWA comparing annual pastures with perennial pastures in a reasonably high rainfall zone. And so the hypothesis was that the perennials, because you've got deep-rooted plants that are there all year round, would, over a number of years, build up the soil organic stock to a greater level than in the annual pasture. What they found was that even sites that were up to 34 years in perennial pastures, there was often very little difference in the organic matter content of those different soils. They also did some modelling, organic matter modelling here, and found that actually under the perennial pasture, if you keep it going long enough, 40, 50 years, you will be able to measure some increase in soil organic matter content, but still not a large amount. And I think that's an important reality check when we're talking about soil organic matter and what's possible and what's not possible. I guess there's two aspects of this. One is if you're just in a production system and you want to know what's happening over time. And then the other aspect is if you're in a carbon offset or carbon sequestration program where you need to be able to measure and validate. So if we're talking about the latter, as carbon sequestration or carbon offset system, there are prescribed guidelines and rules on how you have to sample and what the methodology you should use for the analysis of carbon in the soil. But if you're just in a farming system and you're interested in productivity of the land and what the trends are over time, there are some guidelines there about how many cores you need to take and the uniformity of the area that you need to sample from, and of course sending the and standardizing the depth. We know that organic matter is quite stratified, so the concentration drops quite sharply with depth. So small variations in the depth of sampling that might not seem significant, you only push the pogo stick in to 8 centimeters rather than 10, could end up biasing the organic matter level that you've measured quite significantly. But I think most of the sampling programs for fertility management of soil suggest you need to find a uniform area, and you need to take something like 25 to 30 0 to 10 centimeter samples from that area in order to make sure you've got a pretty representative sample. And then of course you have to make sure the sample either gets to the lab quickly if it's moist, or dry it, sun dry it, air dry it quickly so that there's no further change or breakdown of the sample, and then get it to a lab that is certified and can demonstrate that they're able to produce reliable results. And in terms of the time frame for organic matter, probably 3 to 5 years sampling frequency. I don't think it'd be realistic to expect to measure big changes within 1 or 2 years.
Thank you for watching. If you found this information useful, there are many more related projects to discover at our website. Please like this video and subscribe to our YouTube channel for more Soil CRC webinars, project updates and conference presentations. This webinar series was produced by the Soil CRC, jointly funded through the Australian Government's National Landcare program, to build the technical capacity of natural resource management agencies, Landcare and grower groups to deliver soil health information to farmers for improved soil management. For more information about our projects, visit soilcrc.com.au.